Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
All right, let's take a look at this lesson 5.2.1. This is called System of Equations, and this is bringing us to a new idea that is unique to 8th grade math. So there's a lot of crossover between 6th, 7th, and 8th grade math, but this is a newer concept, but it's primarily built on the same thing we've been working on all year, where instead of just solving a problem that involves one equation, we're now going to have two different equations put together, and we're going to solve problems based on how we work with the two equations put together. So in section 4.1, you graph lines and curves that represented tile patterns. But what happens when you graph two lines at the same time? What can you learn about that situation? Today you're going to use data, graphs, and rules to examine what happens when two lines or curves intersect. Okay, so we're going to start off with a problem, and there is a PDF form that has a graph on the classroom that you can print off that can help you with this process. It says here, the Iditarod Trail sled dog race is famous for its incredible length and its use of dogs. Sled drivers known as mushers start their dog sleds at Fairbanks, Alaska. That's the starting. And ride through the snow for several days until they get to Nome, Alaska. That's the ending place. Along the route, there are stations where the competitors check in, so data is kept on the progress of each team. Joyla and her team of dogs have made it through the first 5 checkpoints. Her buddy Evie, who left Nome on the day the race started in an effort to meet Joyla and offer her encouragement. Okay, so Joyla's at the starting line. She's the one with the dog. She is racing. She is heading toward Nome. Evie, she is in Nome, and I don't think she's got a dog sled. I think she's just traveling on her own along the path that to get her back to Fairbanks. It's the path that the dog sleds would be going on, and her plan is to meet them somewhere along the way. Evie traveled along the route toward the racers on her snowmobile. Oh, there you go, snowmobile. The progress of each person is shown on the graph that follows. So here is the graph that follows. So notice the y-axis is distance in miles from Fairbanks. So 0, 0 would imply that that distance is 0 miles from Fairbanks. So this must be where Fairbanks, Alaska is located as far as the graph is interpreted. And the time in hours is listed on the x-axis. So you can see after 20 hours how far she had gone, after 40 hours how far she had gone, and so on and so on and so forth. So taking a look at this, it says with your team analyze the data on the graph. Well, I just want you to take a look at it and see if you can make sense of it. It says which data. So we've got circles and you've got triangles. One of these is supposed to represent Evie, and the other one is supposed to represent Joyla. Can you tell which one is which based on the information that they provided us over here? Remember, Joyla, she's the one who's starting the race in Fairbanks, Alaska. And Evie left Nome, which is the finish line. So with that piece of information, which one of these represents the stopping points for Evie, and which one represents the stopping points for Joyla? Well, since Joyla started in Fairbanks, and this right here is Fairbanks, she must be the triangles. And Evie must be the circles because, she is farther away. She starts off farther away, and as time goes on, she gets closer and closer to Fairbanks. So when did Evie meet Joyla? Can you tell just by looking at this graph when they would have met? It's not real easy to tell right now, is there? However, there is a reason why we would connect the dots on a scatter plot and create a line out of it. So that's what I'm going to ask you to do. I want you to take a ruler or any kind of straight edge and start at 0 and draw a line that goes through all of those triangles and take it all the way to the edge of the paper. And then do the same thing with Evie and her circles. Put your ruler over top that and then draw a straight line that would continue all the way down to the bottom. When you have completed that, then unpause. And I'm not going to bother pausing. I'm just going to put them in right now. So if you don't want to see me do it and cheat off of me, if you want to know that you've done it on your own, then go ahead and pause right now. I'm going to have Evie be in red. No, Toilet's in red. She starts at the starting point, and if we continue that and a trend, assuming she's going to go at a relative same speed all along, and she has been, the fact that those form a straight line imply that her rate of speed has remained fairly constant. Of course, she's stopping along the way because they're not going to race through the night. Each one of those are stopping points. So they go to a constant rate of speed, stop, camp for the night, and rest. Then another checkpoint, and along the way, since it's a straight line, whenever she was running her dog sled, they were going at a pretty constant rate of speed. And then let's take a look at Evie and see where hers appears to be. I'm thinking to get a straight line out of this data, we probably have to start somewhere around there. So her snowmobile is also going at a pretty relatively constant rate of speed because it's a straight line. So where do they meet? Well, do you see this point right here? That point right there is where they meet. Right, let me do it from here. Right around there is where they meet. And so looking at the timeline for the X line, where does that appear to be? Looks like it's between 80 and 100. It actually looks like it's between 90 and 100. Could be pretty close to 95 or 96. Well, I'm just going to say it's somewhere between 90 and 100 hours after the race begins. That is where they meet. So in this particular situation, the intersection point of the two lines has a very specific meaning. In this case, if I were to just, let me put this in green here, let's call it 96, even though I don't know that that's exactly what it is. 96 hours after the beginning of the race, they met approximately 400, could that be 480, 490 maybe, miles away from Fairbanks, Alaska. So in this particular situation, you've got two different lines, which could be modeled with two different equations, and their intersection point is the one point where that is a solution for both of these lines. That's a point on both lines, which means it's a solution to both of the equations. So now let's go back and start answering more of these questions. How long was this race, and how can you tell? Remember where Evie started? She started at the finish line. So if we go back and look at this line, where does it appear the y-intercept is for Evie's line? It looks to be right here, where x is equal to 0, meaning when the race started, she was in Nome, Alaska, which was at the 11,000 or 1,100 actually, 1,100 mile point away from Fairbanks. So Nome, Alaska must be this distance away from Fairbanks, Alaska. So how long was the race? It must be 1,110 miles. Who's traveling faster? Okay, well, this can be a little bit tricky. In this situation, we're going to have to look at the two lines and look at some growth rates. But can you just look at the lines and tell which one is steeper? Because the one that is steeper is going to imply the greater speed, okay? So if I were to take 2 points, in fact, let's go ahead and use this as our approximation. We can figure this out. We can get a relative or an average rate of speed for both of these people by looking at their growth rates, because that's really what the growth rate is. If you take our formula for speed, where distance traveled is equal to rate of speed times time, and then you divide both sides by the time, that's the ratio that we have here. If you take your distance traveled divided by the amount of time that you were traveling, that gives you your rate of speed. So that's the information we have here. This is the distance traveled. This is the amount of time it took. So if we take that divided by this, your slope ratio ends up being your rate of speed, your growth rate. So I'm going to go ahead and work that out, but let's just see. I'm going to prove it, but can you tell which one looks a little bit steeper? I think the blue line looks a little bit steeper, right? So that would imply that Evie is traveling at a greater speed with her snowmobile than Toila is with her dog sled. I'm going to pause and I'm going to do some calculations here, and I'll write them in here and we can compare them. All right, so take a look at what I've done here. I think the blue line is a little bit steeper than the red line, which would imply that Evie is the one that's going at a faster speed. We can prove that by saying, okay, she started at 0, 1,000, and then they met at 96,490. So that means if I take 1,100 minus 490, that's the number of miles traveled. And while it says negative, I'm going to erase the negative because we are talking about a distance. It did go down. The value for y decreased. So that's where we would put in like that negative growth rate that we learned in chapter 4. But because we are putting this into context with distance, we're just going to call it 610 miles is how far she traveled over 96 hours, which averages out to about 6.4 miles per hour. Then Evie, we know she traveled the same amount of time, but she traveled only 490 miles, right? Because Evie, she traveled a greater distance, but this is where they met, which was at the 490 mile marker. So that's how far Joyla had traveled. So you take 490 divided by 96, and that gives you about 5.1 miles per hour. So that justifies the fact that Evie is the one who's going at a faster rate of speed. The line is steeper, but I just justified it using numbers. Okay? Hold on for a second. Let me check something. Okay, I just realized that I had written some information here that was the justification for how you could tell that, Evie's graph has a y-intercept of 1,100. She started at the finish line, so that's how can you tell for how long was the race. All right, so approximately how long did it take Joyla to finish the race? How are we going to figure this out? Well, let me pause and erase all this work that I've shown here now, and I'm going to draw a line for the finish line. Okay, hold on for a second. Where are you? Okay, so we all agree that Evie started at the finish line, which means the finish line can be represented by this green line that I put across the top. So if we know that Joyla is traveling at a constant rate of speed, after she meets up with Evie, I'm presuming Evie's going to turn around and she's going to go back to Nome, Alaska, maybe following her along the way, going at her rate of speed. So this point right here on the graph is going to be when she would finish cross the finish line. So let's go ahead and figure out what is that. That would be where the time is 220 hours, correct? So, I mean, give or take, plus or minus, it's going to be about 220, maybe 230. Let me actually look at this a little bit more. Maybe that should go a little bit more to the right, somewhere in that range. I don't know. Maybe I should have said 200, 220, about 220. That's a better answer. About 220 hours. That's what we said originally, or what I said anyway, and I'm always right. So there you go. So there it is. That's how we can use the graph to predict how long it will take before she finishes the rate going at this constant rate of speed. Now, if I wanted to, I could create a rule here. So what did we say? She was traveling at approximately 5.1 miles per hour, and she started at 0, so we're not going to bother with the plus 0. If I then take and multiply this times 220, that should give me something pretty close to 1,100. But I don't want to do that. Let's go in the other direction. Let's say if I know she's got to travel 1,100 miles, let's solve for x. If I take her average rate of speed and divide the distance by that rate of speed, I should get the time, right? So that brings us back over to here, where if you take the distance divided by the rate of speed, that will tell you how much time it should take. So what is 1,100? 1,100 divided by 5.1. It actually is 215, so I'm glad I didn't say 230. I'm saying it's closer to 215, but that was a rounded off average rate of speed. So it would be 220 if her average rate of speed was 5 miles per hour, if we rounded it down to there. So anywhere from 210 to 230, somewhere in there should be her time that it takes her to finish this particular race based on the information on the graph. All right, so the points where two lines or curves cross is called the point of intersection. Two or more lines on this, for the same situation on the same graph are referred to as a system of equations. So what we're going to do next is we're going to take these two equations. Please write this down, and I want you to graph them both on the exact same coordinate grid. So you'll want to make your coordinate grid look something like this. Now, if you feel comfortable graphing these without using a table, please do that. It'll save you time. But if you want to set up a table and find your ordered pairs and then plot those ordered pairs, go ahead and do that. Please make sure, though, that you're labeling at least 3 points, and please label the intersection point. I'm going to pause and finish it. You pause as well. All right. Is this what your graph looks like? So I decided to use my growth rate and my y-intercept to graph this one. The y-intercept is at -4, since b is equal to -4, and my growth rate is going to be 3/1 because 3 rise over run, up 3, 1 to the right, up 3, 1 to the right, up 3, 1 to the right, and so on and so forth, and I label at least 3 points. For the blue, we've got a growth rate which is -2/1, and our y-intercept is at 6. So here's our y-intercept, and we're going to go down 2, 1 to the right, down 2, 1 to the right, down 2, 1 to the right, and so on and so forth. Well, do you notice right here what we get? We get an intersection point. So that is our solution to the system of equations. The point where is on both of the lines, the intersection point is at 2, 2. So the significance to this is that this is the point that represents a solution to both equations. It's the only point, the only values for x and y that both of these rules would share in common. And so we can prove that by plugging this number into each one of the rules. So when x is equal to 2, that becomes 3 times 2 is 6, and the y becomes a 2. And 3 times 2 is 6, 6 minus 4 is 2, yes. We see that when x is equal to 2, y is indeed equal to 2. And here, let's plug that in again, where it becomes -2 times 2 plus 6 needs to equal 2. And what is -2 times 2? It's -4. -4 plus 6 is equal to 2. So this proves that 2, 2 is in fact a solution to both equations or both rules. So it has to be a point that is on both lines. And the only way it can be on both lines is if it is the intersection point. So what we are learning from this situation is when you've got two rules for two situations where the x and the y represent the exact same thing for both situations, the intersection point on the graph tells you some very important information. So here is where we get a chance to analyze some graphs and look at their intersection points. So graph A has the time of year on the x-axis and the temperature on the y-axis. Notice that Rio de Janeiro starts out with a higher temperature and then starts to decrease as you go into spring and closer towards summer, because they are in the southern hemisphere. So when it's getting summer toward us, it's getting winter for them. San Francisco starts out cooler in our winter, but it's going through spring and warming up to summertime. So what does this point represent there? Let's take a look at B. Before we answer those questions, I'm going to pause, have you analyze what you think that point means and write a short statement that I will reveal once I unpause. Here you've got the cost to produce some tortillas. So the traditional way of making tortillas is you have someone in the back kitchen making all the tortillas, right? You make them by hand. But if you purchase a machine, then it's going to cost a little bit more at first. But as you manufacture more tortillas, the machine starts to become more efficient, so the cost to produce it goes down over time. What does that point represent? For this, you've got pollution as your y-axis and population levels is your x-axis. So you expect in both situations, the higher your population, the more pollution you're going to have around your city. So here are the two cities, Boston and Denver. What's going on here with their population levels compared to their pollution levels? And what does that intersection point represent? And then for D, the distance from the starting line, here's the tortoise. Looks like the hare waited a little bit because the hare is still at the starting line while time is passing. So tortoise has started moving, and then hare starts a little bit later. So tortoise got the head start, and then hare appears to be going a little bit faster. What happens at that intersection point? Go ahead and pause and write down a brief statement for what each one of those intersection points represents. All righty, we ready for the reveal? What do we have happening here? Looks like at a certain time in spring, both the temperatures of Rio de Janeiro and San Francisco are about the same, because it's kind of like, what's the temperature on April 1st compared to August 1st? Around here, I think it's a little bit hotter. No, not August. That would be October, wouldn't it? Around here, October is a little bit warmer than it is in the springtime, but apparently in Rio de Janeiro, those same relative times on their calendars are about the same temperature. Here, this is telling us that after a certain number of tortillas have been manufactured, the cost to produce them is about the same. So however many this is, that's when the cost would be the same. But beyond that is when the machine starts being more efficient and more cost effective. Here, at a certain population level, Denver and Boston are going to have the same level of pollution. I'm getting tired. This is my third one I've done today. I need to stop. And then here, this intersection point represents the time it'll take before the hare catches up to the tortoise. Okay, so every one of these points on these graphs has a specific meaning. The intersection point of two different lines has a very special meaning given the context of that particular problem. And we're going to explore deeper into that with our problem solving once we get into a little bit deeper into this chapter. So, all right, so let's go ahead and close this down. Time to move on to our next activity. Take care.
Hey, feeling good.